This is a list of growth functions that you will commonly see when analyzing computer programs, listed in order from smallest to largest. Now, some of these are more common than others. The first of these isn't even really a function, it's just the value 1. What this means in the context of a computer program is that the runtime of the program does not depend on the input size. Now, this doesn't mean that the program is slow, it simply means that the execution time does not grow with the size of the input. This is also known as constant time. Next we have log of n, and then log n, and then log squared of n. Now all of these logarithms are assumed to be base 2, so this here log n is assumed to be log base 2 of n. However, I'll demonstrate at the end of this video why the base isn't really irrelevant when discussing big O. You may also find this notation here curious. This log squared of n is simply equivalent to the quantity log of n squared. But we can't write this without the parentheses because then the n would be squared, and so we move the squared next to the log rather than having to write this parenthesized quantity all the time. Of these three categories, this one here, where it's a plain log, is certainly the most common, and this is simply referred to as logarithmic. Next we have n by itself. This is what you typically get with a standard loop that executes some n number of times, and so this is linear. Then we have n times log of n, and then n squared. This is quadratic. And n raised to the 3 is cubic. And I won't list any more out, but obviously if you increase the exponent, you'll get larger and larger runtimes. So n to the 4 is greater than n to the 3, n to the 5 would be greater than that, and so on. But all of them, no matter how big that exponent is, if it's a constant value, it's going to be less than 2 to the n. And this is an exponential function. Now, I won't list all of these out, but 3 to the n is larger than 2 to the n, 4 to the n is larger than 3 to the n, and so on. So as we increase the base, we get larger and larger functions that take longer to execute. This last one is factorial, and in case you forget what this notation means, it just represents n times n minus 1 times n minus 2, going all the way down eventually to 3 times 2 times 1. And so this is factorial. And of the functions I've listed, this one is definitely the worst. So hopefully in your code you'll avoid these really expensive functions, but sometimes you can't. So given this order, what it means is that if we write out a function that contains several of these sort of functions as subfunctions, that all we need to do is focus on whichever one is largest. And also we can ignore coefficients. So if I have a function like this, this function contains n cubed, n squared, log of n, and a constant term. But this is big O of n cubed, because n squared is less than n cubed, the log n is less than both, and the constant is less than all of them. And we get rid of the coefficients. This is the coefficient for that term, this is the coefficient for that term, that's a coefficient. So those are irrelevant in the simple big O functions that we tend to use. And here's one more example. So in this function, 2 to the n is the portion that grows the fastest, and therefore the big O of this is 2 to the n. Now at this point, a bit of caution is needed in terms of how we speak of these functions. I said here that this function is O of 2 to the n, and this function is O of 3 to the n. Those statements are true, but if you think back to the strict definition of big O, all it is saying is that if you multiply this function by some constant, it will be larger than this function when the value of n is sufficiently large. Now, technically, what that means is that this first function, although it is true that it is big O of n cubed, it is also O of 2 to the n, and it is also O of n factorial, because these are also upper bounds on that function. So anything that is larger also qualifies as an upper bound. However, it's generally understood that when we talk about big O, what we care about is the tightest bound, the smallest function. So although it is true that this function is O of 2 to the n, that is a worthless piece of information. What matters is that it is O of n cubed, because that is the smallest function, at least among these functions we will commonly see, that actually tells us something worthwhile about the runtime of this function here. So whenever we talk about big O, we always care about the tightest possible bound, the smallest bound. The strict definition gives us leeway to pick some arbitrary large function, but that's not useful. So we want to pick the smallest function for which our claim about big O is still true. So the fact that when you add a bunch of these functions together, all that matters is the one that grows the fastest can actually be formalized with a theorem. So this theorem says that if f sub 1 of n is O of g sub 1 of n, and f sub 2 of n is O of g sub 2 of n, then if you have a function that combines those two subfunctions, f1 of n plus f2 of n, then this is going to be big O of whichever of those two g functions is largest, the maximum of g sub 1 of n and g sub 2 of n. So an example of this is if we have 5n cubed plus 2 log n. Well, in this example, this 5 times n cubed will be our f sub 1 of n, and this 2 times log n would be our f sub 2 of n. Now, we know that 5 times n cubed is O of n cubed. So we're going to say this is O of the max of n cubed. And 2 times log of n is O of log n. So that is our g sub 2. So this here is g1 of n, and the log n is g2 of n. And so the larger of those two is the n cubed, so it's actually O of n cubed. Now, this example I just did actually relies on another theorem, which is fairly obvious, but is worth formally stating. If f of n is O of g of n, then that means that some constant k times f of n is also O of g of n, basically indicating that constant multiples are irrelevant because the definition of big O allows for us to define some constant already anyway. So this would just sort of be copied over into the definition. So this is fairly straightforward to prove. I won't elaborate on it more. But this claim here is the reason that 5 times n cubed is O of n cubed. Here's another useful fact. If f sub 1 is O of g sub 1 and f sub 2 is O of g sub 2, then that means that the product, so if you multiply f sub 1 of n times f sub 2 of n, then the big O of that is the product of the two g functions, g sub 1 of n and g sub 2 of n. So an example of this would be if I had something like 5n squared plus 7 quantity times 7 log n. So I'm multiplying these two together, but the big O of this would be n squared log n, because if this is our f1 of n, then n squared would be the g1 of n, because 5n squared plus 7 is O of n squared. And if 7 times log n was our f2 of n, then log n by itself would be our g sub 2 of n by this previous theorem I mentioned here, where the constant k in this example is 7. We can apply these concepts to actual code as well. So here we have a rather large Java method, and we want to know what the overall runtime of this code is. So first, I want you to note that we have this for loop here and this for loop here. So whatever the runtime of this method is, it's going to be the time for this portion added to the time for this portion. So we're basically just adding those together. The other thing I'm going to point out is that we have a nested loop. We have this loop inside of this loop. So if we can figure out what this loop is in isolation, and then we can figure out how many times this loop repeats, then that is essentially multiplication. So first, we want to look at how many times this loop runs. Now, before we focused on counting individual statements, but I think it's clear at this point that what really matters is simply how many iterations we have, how many loop repetitions actually occur. And we can even be a bit vague as to the exact number, because if we add 1 or minus 1, it's not going to affect the terms we care about, because we want to know the growth behavior. So getting it down to the precise number of statements is not as important when all we care about is the big O. So this loop starts for I equals 0, I is less than n, but, extra complication, I plus equal to 2. That's a little bit different, but not in a way that really matters. If we were simply doing I++, then it would be obvious that the loop runs n times. But if we're doing I plus equal to 2, well, that means we'll loop fewer times, we'll reach our termination point faster, but all we're doing is splitting the number of iterations in half. So this loop will run 1/2 of n times, roughly. So I'm going to put 1/2 n as the count for this. And then there's a statement there which we could ignore, but I'll go ahead and include it just for now. And then we have this loop. And this is actually something a little bit different than what you've seen before, because we loop as long as k is greater than 1. That's not surprising. But the variable update is k divided by 2. So k is set to itself divided by 2. And so what is the runtime of this loop? Well, it turns out that this is actually a very common way of getting logarithmic behavior. Because if we start off at n and we keep dividing by 2 until we reach 1 or 0 or some other small value, we have to increase n by a lot to get one extra loop out of this. So the number of iterations of this loop here is roughly log of n, specifically log base 2 of n, because we are dividing by 2. Then we move on to this next loop. This loop goes from I equal to 1, I less than or equal to n, I times equal to 3. And so this is actually another common way of getting a logarithmic loop. Now technically, because we are multiplying by 3, this is log base 3 of n. But I'll demonstrate in a moment why that distinction doesn't matter. It was mentioned earlier that we assume all of our logarithms are base 2, and there's a theorem I'll show you that says that log base 3 of n is O of log base 2 of n. And so if we take all of this as given, what we essentially have is a function that is something along the lines of 1/2 n times quantity 1 from this plus log 2 of n and if we wanted to account for the fact that there's the test and then those two statements, we could multiply this by 3. Once again, it's all going to disappear in the end anyway. And so that's a quantity, and so this takes care of the entirety of this loop with an inner loop, and that's being added to this result here, the log base 3 of n. But we can figure out the big O of that by just looking at the individual components. So we know that 1/2 n is O of n. We know that this complex little function here is O of log base 2 of n, or simply log n. And I already mentioned here that log base 3 of n is O of log 2 of n, or simply log of n. Given those facts, we can apply both the rule about adding functions and the rule about multiplying functions to see that when we multiply these two together, that bit is O of n log n. And we're adding a log n, but n log n is more than log n, so it's irrelevant. It just reduces down to this. I guess the step that I'm skipping is that this is the max of n log n and log n, but that means that the final result is simply O of n log n. So all of this code here has a runtime of n log n, and it's primarily because of this, because this portion will take longer to run than this portion, so this portion controls the growth behavior of the function, whereas this is subsumed by the longer running portion here. So why is log base 3 of n O of log base 2 of n? Well, this actually relies on an even more general fact that log base anything of n is O of log base anything else of n. So keep in mind that a and b here are both constant numbers. But what this means is that a could be 3 and b could be 2. It also means that a could be 2 and b could be 3. So log 2 of n is O of log 3 of n, but it's also true in the opposite direction, which is kind of weird, but we're going to prove it. It actually hinges on this change of base formula for logs, which you can be forgiven for forgetting. It looks like this. Log base a of n is equal to log base b of n divided by log base b of a. And remember, very important in all of this, that a and b are constants. Now what that means is that this portion, log base b of a, is the log with a constant base of a constant value. So that is also a constant. And the fact that this is a constant makes proving this fact here fairly straightforward using the definition of big O. So we'll start with the function on the left. And we want to show that this is less than that quantity multiplied by some constant. Well, according to this change of base formula, it's equal to this, but when we're dividing by a value, we could simply rearrange things so that we have 1 over that value multiplied by the thing on top, the numerator. So this will be true for any constants a and b. And so what that means is that this is equal to c times log b of n for c equal to 1 over log base b of a. And we're defining a constant, but this is allowed because log base b of a is constant. The only thing we're missing is our value k. And technically we proved equality, but if it's equal, then it's also less than or equal as well. And this is going to be true for anywhere that the logarithm is defined, although logarithms are only defined for values greater than or equal to 1, so our k equals 1. And so that's why all logs are equivalent for the purposes of big O.